Hello viewers, welcome back to the course on matrix computation and its application. So, in the previous lecture we have discussed about the basis and the dimension of a vector space, and in this lecture we will continue with that one. So, let us start with this. So, this is lecture number 14. Now, so in the previous one we have discussed that if I have a set S which contains n number of elements and that S spans the whole vector space V, then any subset of V any subset of V cannot have more than n number of numbers of linearly independent vectors. So, that we have seen. Now, there is a corollary. So, in this corollary it says that if V has a basis, if the V has a basis of n elements, then every set of p vectors with p greater than n is linearly dependent. So, that we also seen using the one example, because the V has a basis which contains n elements. It means that V is n dimensional, and then every set of p vectors with p greater than n is LD. So, that we have already seen also. Now, after this one we can have some another corollary. If the vector space V has a basis of n elements, then every other basis of V also has n elements. It means if one basis has n elements, then if I choose any other basis that also contain n element. So, the proof is, so let us take basis B1, suppose that contains V1, V2 up to Vn, and I take B1 and B2 that contains W1, W2 up to Wm. So, let take B1 and B2 are the two bases of vector space V, that is B1 spans V and B2 also spans V. Now, we have to show that n is equal to m. Now, since B1 spans V and B2 is W1, W2 up to Wm is Li. Then using previous theorem, we have that m will be less than equal to n. In the previous theorem we have discussed. So, this is the first one. Second one, similarly B2 spans V because it is a basis. So, if it is a basis, definitely it will span, and B1 that is containing V1, V2 up to Vn elements is Li. So, it spans V and this set is Li, which implies that V, which implies that n definitely will be less than n. So, from these two conditions, so from 1 and 2 we get m is equal to n. So, if I choose any two bases, then they will contain the set will contain the same number of elements in that basis. So, this is the proof we have done. Now, so after this one we can discuss about the standard basis. So, standard basis we can discuss, like we have a Vn. Vn is the, we know it is a vector space, and Vn contains all the elements like this one x2, x1, x2 up to xn, so that each xi belongs to real line. So, this is vector space over the real line, that we already know this one. Now, in this case we can define the standard basis. The first basis I can define as E1, that is I can write 1 here and 0 0 0. Another I can define the vector 0 1 0 0, so on, and in the last I can define En that contains 0 0 0 1. So, this all belongs to Vn. Now, how they are the standard basis? Now, we can check the set E1, E2 up to En. So, this is the set is Li. So, why it is Li? Because the corresponding matrix will get 0 1 0 0 0 up to 1. So, you will get only unit matrix or identity matrix. So, we call it. And this is always invertible. So, in this case this is this matrix identity matrix. So, which implies that this set of vectors are linearly independent. So, the first claim is over. The second one is that the set E1, E2 up to En spans Vn. So, that is very easily we can show that. Let we take a vector say x1, x2 up to xn belongs to Vn. So, in this case I can write x1 x2 to xn. This can be written very easily like x1 1 0 0 plus x2 0 1 0 up to 0, x3 0 0 1 and xn 0 0 up to 1, and maybe I can write x1 e1 plus x2 e2 xn en. So, this vector can be written like this one, and this is unique. So, we can write this uniquely. So, from here I can say that it is linearly independent and it spans Vn. So, from here I can say that the set this E1, E2, En is a basis of Vn, and we call it standard basis because it contains only one non-zero element and all other elements 0. So, that we can always use if somebody asks about some basis of any vector space, then we can, the simplest basis we can have is the standard basis. Now, so after discussing this one, what about the vector space P and X, where x belongs to some interval I. So, we know that P and X is a set of all polynomials with degree less than or equal to n, and x is coming from the interval. So, we know that it is a vector space. So, in this vector space, the standard basis now, if I take the element, any element from here, so let me choose, let me write a0 plus a1x plus a2x square up to an xn. So, this is the polynomial I have from here. So, let it is, I call it Px. So, in this Px, you know that it contains n plus 1 number of coefficient. So, this I can write as a0 an xn. So, this I can write as a0 plus a1 and then x plus a2 x square plus a3. So, this is just a vector I am taking a3 x3 an x power n. So, from here you can say that if I choose any vector from here, then I just take a set containing the element 1 x, x square, x cube, x n. So, this is a set, I call it, maybe I call it P. So, this is a set that belongs to P and x, because 1 is also belongs to P and x is also belongs to P and x, and if I take any element from this P and x, it can be written as a linear combination of these vectors, and this is the simplest one. So, from here I can say that this is the standard basis for the vector space Pnx, and from here, and this vector contains n plus 1 number of elements. So, from here I can say that Pnx is a n plus 1 dimension. Space. So, it is n plus 1 dimensional vector space. Now, from here we can define I can define the terminology finite dimensional spaces, finite dimensional vector spaces, where, so these are those whose basis contains finite number of elements, like we have seen Vn and Pnx, like this one, and another is infinite dimensional. Where basis contains infinite number of elements. For example, if I take the vector space of all the continuous function defined from minus infinity to infinity, or I take the space C1 defined from A to B. So, set of all the continuously differentiable function whose derivative is also differentiable, or whose derivative is also continuous and defined from A to B. So, this is C1 AB, this is C minus infinity to infinity. So, all these functions make the vector space, and this is infinitely dimension, because they cannot be represented by finite number of elements from that set. So, these are called the infinitely dimensional spaces. Now, from here there is one more result, that in a n dimensional vector space V, any set of n linearly independent vectors is a basis, because if it is n dimensional vector space, then you take any set which contains n linearly independent vector, and that vector, that set will be a basis for that vector space V. So, this is, we can see very easily. It means that, which implies that, suppose I take Vn element, Vn set. So, this is n dimensional. So, if I take a set as which contains n number of elements, V1, V2 to Vn, and this set is linearly independent, then I can say that S is a basis of Vn. So, if it is linearly independent, then it will span the whole vector space Vn. So, that is why we call it that it is also a basis of this one. So, once they are linearly independent, that is enough that this spans the whole Vn, because it is n dimensional space. So, this is just the application of the previous theorems based on this vector spaces, the dimension and the basis. So, it is understood. We have also given lot of example based on this one. Now, after this one more terminology we want to use is that theorem that in a vector space V, let I take a basis B spans V. Then so I just write a set B which spans V. I do not know whether it is a basis or not. Then the following two conditions are equivalent. The first one is the set V1, V2 up to Vn is linearly independent. So, it spans V, that is okay. Then I can say that V1, V2, Vn is Li, or I can say that if I take any element V from V, then the expression V is equal to alpha 1 V1, alpha 2 V2, alpha n Vn is unique. It means that if I write this expression, then this alpha 1, alpha 2, alpha n all are unique. Only one representation is there, that we can write V as a linear combination of V1, V2 up to Vn. So, this is unique, or maybe I can say that alpha 1, alpha 2, alpha n are unique. So, either it is Li or it is unique, both things are same. If it is Li, then it is unique, and if it is unique, then definitely it is Li. So, just it can be seen very clearly because it spans this one. So, if it is span, then any element from V can be written a linear combination of this one, and if this is linearly independent also, then we have seen that the corresponding matrix we have seen that is non-singular, and we can have the unique solution. So, in that case the representation will be unique, and if the representation is unique, then it is linearly independent. So, we can just understand from this one, and it is up to the viewers to understand and to do the proof for this one. It is very simple. Now, after this one, let us do few examples based on this. So, let us write some question. Suppose I said that I have a set S. So, this is example. Let I take the set S which contains x minus 1 and x square plus x minus 1, x square minus x plus 1, and suppose my vector space V is P2. Okay. So, I want to check S is a basis or not. So, this one we have to check, and now I am taking the V as P2. So, P2 means set of all the polynomials of degree less than equal to 2. So, this one I want to check. Now, first we need to check S is linearly independent. So, for this one what I am going to do is I will take A x minus 1 plus B x square plus x minus 1 plus C x square minus x plus 1, and then it equal to putting equal to 0. 0 means 0 polynomial. But here we okay, let us solve this one. Now, this is true for all x belongs to the interval. This expression is true for all x belongs to the interval. Otherwise, if you put like this one, then maybe you can find the roots, but the condition here is that this is true for all x belongs to A. So, if it is true for all x, implies that the coefficient should be same for left hand side and right hand side polynomial. So, from here, which implies that now I can choose the terms corresponding to x square. So, it is B plus C. Now, from here I can write B plus C x square, that is I can find. Then with respect to x, I can write A plus B minus C x plus the constant term. So, I can write here minus A minus B plus C equal to 0. So, this one I can write. From here I can write B plus C is equal to 0, then A plus B minus C equal to 0, and from here I can have minus A minus B plus C equal to 0. Now, from here this one I can write expression as A plus B minus C equal to 0, and that is already there. It means this system is, because corresponding to x is A plus B minus C, and this is minus A minus B plus C. And this is both are same. So, it means I have a system of equation that is B plus C equal to 0, A plus B minus C equal to 0, and A plus B minus C equal to 0. So, this one equation is redundant equation. So, from here I can say that this is the matrix with the rank 2, because if I write the matrix corresponding matrix, so it is 1 0 1 1 1 1 minus 1 and 1 1 minus 1 A B C equal to 0 0 0. And from here you can check that this matrix cannot be, so A x is equal to 0 and rank of A in this case is always less than or equal to 2. It cannot be 3, because just I can reduce this last row as a 0 here, no problem. And from here I can say that A is singular, and which implies that the set S is linearly dependent. So, if it is a linearly dependent, then from here I can say that the set S is not a basis for P2, because if it is not a Li, then from here we can say that this set is not going to be the basis for this one, because for the basis it should be linearly independent and should span this one. So, first condition is not satisfied. From here only we can conclude that this S is not the basis for the set of polynomial of degree less than or equal to 2. Okay. So, from here, so I think we can stop here. So, today we have discussed about the meaning of finite dimensional spaces and infinite dimensional spaces and discuss few examples. So, in the next lecture we will continue with this one. So, thanks for watching. Thanks very much.